Hi. So today I'm going to talk about a project that two of us have worked on. It's called Deferred Rendering. So we have our Prime Engine source code in which we have the normal forward rendering approach going on for the scene, and we wanted to implement a deferred render from that. So let me tell you how normal forward rendering works. So this is an example pixel shader, and we get the diffuse color from the texture coordinates, and then you have the input structure of the pixel input structure. You get the normals, you get the positions, and so using all this information you calculate the lighting. So this is our function for calculating the lighting equations, and then you output a color. So that is how forward rendering works. In deferred rendering, we do not calculate the lighting immediately, but we use a different pixel shader. For example, this. So we get the position and we get the normal and we store it and we just return the positions and the normal. So basically, we create textures which contain the positions, the normals, and the diffuse color information. And using that, we calculate the final color in a final in a separate pass. So in a deferred renderer that we are using, we are having three passes. So first pass calculates the position and the normal x, and the second pass calculates the albedo color and the normal y. So using these two passes, we can get the color, the normal, and the position. So we have a third pass, which I'll get into later on. So let's just go a little more into detail in the shader exactly what we're doing. So this is the normal, this is the diffuse color, and then we have the normal. So we have to transform it from -1 space to 0 1 space because the textures can only store values of between 0 and 1, and we just set the y coordinate. And in the other pass, we have the positions. Again, we transform it from a -50 to 50 range. That's what our scene has, the positions in our scene has. We transform it from that to 0 1. So we have some precision loss because of this, and we will see some artifacts in the scene later on. So, and we also have the normal x. And in our shader, what we do is using the normal x and the normal y, we calculate the normal z. So this is what we're doing here. So okay, this is our deferred render pixel shader in which we just sample different textures. So this is the texture that has the position and the normal x. This is the texture that has the albedo color and the normal y. And this is the third texture that I'll get into. So these are the textures that we use, and then we calculate lighting in a 2D space, just the screen space pixels. So let me show you how this works. So I'm loading up the level, and this is the output in the normal forward rendering approach first. So we have a number of objects, quite a few actually, about 1 2 3 4, it's hundreds of objects, and we have a light shining on each of them. Not all of them, some of they have multiple lights and multiple objects. And so this is how the forward rendering approach. We can see the frame rate varies, but we also have average frame rate is about 20 right now. So what we can do is we can select a rendering mode of one, which is for deferred rendering approach. So as soon as I do this, so we see the lighting changes slightly, but we still have the same number of lights and the same objects. So this is running in deferred render mode, and we can see the frame rate has picked up. What's about 33. So what we can see how this is happening. So this is the pixel shader that we're using. So let's say instead of doing the regular calculations, I'm just gonna, so this is the position that we're getting, and we calculate. So where we have, this is the world position. So let me just return the world position as a color. So then we'll see what's happening here. So let me reload the pixel shader that I've changed. So that's the world position. So that's just all the objects colored using their positions. And we have the normal. Let's see how the normal works. So these are all the normals of the objects. And finally, we have the albedo color itself, which we get from here. So I'm just going to copy that and paste that. So albedo. So that's the albedo color. So these are the three textures that we have basically, and we are using these to calculate the lighting, which let me just uncomment this so that the rest of the lighting here, this is where all the lighting calculations happen with using these three information. And let me reload, and that's my deferred rendering lighting output. So this is a graph of the average frame rate. So we can see initially it was forward rendering and then picked up as the deferred rendering started. And these are the peaks where you were just showing the normals and the position values. So there was no lighting calculation being done. So that was the deferred rendering approach. And we also have a mode to see the lights. And, yeah, select two. So we have a multiple spotlights in the scene, and these are the spotlights. Each spotlight has been modeled as a pyramid. So, and here we are just drawing the lights as geometry. This is to visualize what are the areas in the scene that have been lighted by light. So ideally we would only calculate lighting for these areas in the pixel shader, in our deferred rendering pixel shader. Right now, we are actually calculating lights for all X resolution by Y resolution pixels, but in our code, we can go ahead and do this instead. So this is the light region. So I did not show the light region texture. This is the third pass that I was talking about. In the third pass, we just output the lights. So in my deferred rendering shader, if I output my light values, let's see how that looks. Select rendering mode and then reload the pixel shaders. So this is the same view that we had earlier. So these are the lights. And then what I can do is I can only calculate the lighting equation if the lighting region has a valid value. Like if this is dark, then we'll not calculate lights. If the red value is greater than 0.5, we calculate the lights. So let's see how that goes. So this is, I've changed this so that we only calculate the lighting wherever there's a valid light. So that's that. And this actually gives us slightly higher performance than without using the lighting area. So as you can see, that's that. So we actually have a graph here with some of the results that we've calculated. So this is on the y-axis, we have the average frame rate, on the x-axis we have the number of lights. So when the number of lights are small, the FPS that we get is similar for forward rendering and deferred rendering. As the number of lights increase, we can see a divergence. So the frame rate of forward rendering drops drastically, whereas the frame rate of deferred rendering doesn't drop that bad. So the orange is the frame rate without using the lighted area. Basically, we calculate light for all pixels, X resolution by Y resolution, and the purple line is where we actually use the lighted information. So that's a simple different render we have made. Definitely, there are a lot of improvements we can do, and we will try to keep doing that forward. Thank you for listening.